Okay, so now let us go and solve this problem over here. Like always, I want to remember the procedure. Step 1, you read the problem statement, you do some type of figure and summarize the input and output. Step 1, you do the diagram that be used in order to write down the main equation in step 2. If you need more equations, you go to step 3. And finally, once you have enough equations, you go and solve the problem in step 4. Okay, so let's read this problem over here. A piston cylinder. Okay, so I stop right there and I do the figure of a piston cylinder. Contains air. Okay, so as I read the problem, piston cylinder assembly we know will be a closed system. Air we know will be an ideal gas of mass 0.15 kilograms. So that gives me time to think about the problem. Of air initially, so let's say here, let's say we know initially at 2 megapascals and a temperature of 350 degrees Celsius. Okay, the air is very expanded, so we have an expansion here isothermally, so that means that T2 will be equals to T1, and we know the pressure P2 will be equal to 500 kilopascals. Alright, then is compressed. Compression polytropically, so that means that, and they give us here the values will be PV to the 1.2 to the initial pressure, so I guess it's P1, so P3 will be equal to P1 to the initial pressure. And okay, one more compression, and finally we have another compression at constant pressure, so it will be P1, P2, P3, P4. So P4 equals P1, and that's basically what we have. Okay, so this should be step 0. Step 1, what I would do here is another small figure of this one, just showing that this is my closed system. Alright, and now when you have different processes, okay, or even if you only have one, always good to do the PV diagram. So over here, since we're missing a lot of data, we're probably going to have to do a bunch of calculations before we get to the final figure. But let's see, it looks like it's an expansion, so we should be here, and then it's going to go back. So let's say, let's guess. Let's say initially we'll be here. This will be 1 and P1 is going to be expanded, so we know V2 will be higher than V1, and we go to a pressure P2 of 500. So they tell us that it's an isothermal expansion, and every time there's an isothermal expansion compression, any type of compression expansion, if they don't tell you it's a polytropic with a certain value, in most cases you can assume that this also will be an polytropic expansion, but with PV equal to a constant. So this will be 2. Alright, so I make some type of line. So we know P1, we know P1. Okay, so slowly, we're going to go slowly here. So can we calculate what is the initial volume? Since we know air is an ideal gas, we can use the ideal gas relation. P1 V1 equal to N R bar T1. And here we can solve for V1 will be equal to N R bar T1 divided by P1. Alright, so we know, so now the value of R, here I'm using the Zengel table, so that will be on the conversion factors table over here. Might not be very clear on video, but it would be page 984. And R bar over here is equal to 8.314 kilojoules kilomole Kelvin. Okay, and for air, you might remember or not, but again for the single textbook will be table A1 on page 882, and the molar mass of the air is 28.97. All right. So now we substitute into this equation here. That would give us what? So we know the mass is 0.15, but N would be the number of moles, so the N number of moles is equal to what? Mass divided by molar mass. So the N is equal to 0.15 divided by 28.97. Now we're going to multiply by the R, which is 8.314. Okay. And T1, remember the units here are Kelvin. We have T1 in Celsius, so we need to do 350 plus 273 divided by P1, which is 2 megapascals. But look at the units, we have kilojoules, so we need to transform the 2 megapascals into kilopascals, so that will be 2000 kilopascals. And if you do this calculation, you will get about 0.0134 cubic meters. Okay? So we can do a similar calculation for P2 since we know the pressure at 2 and the temperature at 2. So if we do the same thing, we can have P2 V2 equal to N R bar T2, which will give V2 equal to N R bar T2 over P2, and that would be equal again, basically the same thing, 0.15 divided by 28.97, 8.314. Temperature is the same, we know what's an isothermal process. The only thing that changes is the pressure, so this time would be 500, and that gives us a value of 0.0536 cubic meters. Okay, so now that we made it this far over here, we need to see what happened for process 2 and 3. So again, we know it's a compression. We know P3 will be equal to 2 megapascals. We know it's a polytropic process. So maybe we can find what would be V3. Okay, so in order to do that, process 2, 3, we'll know that P2, V2 to the 1.2 will be equal to P3 V3 to the 1.2. So if we solve, this will be equal to what? P2 over P3 will be equal to V3 over V2 to the 1.2. So this will give us that this is equal to P2 over P3 to 1 over 1.2 equals to V3 over V2. So that V3 will be equal to V2 P2 over P3 to the 1 to the 1.2. Alright, so this will give us that V3 will be equal to what? So we know V2 to be equal to 0.0536. P2 is equal to 500. P3 equal to P1, so it will be 2000 kilopascal. Remember, this is the 2 megapascals to the 1 divided by the 1.2. And this is going to give us a value of 0.0169 cubic meters. So basically it's a lot of work just to get some figure going on. So let's see how the figure will look like. So we know that V2 is equal to 0.05, so 0.01, 0.05. So this one should be somewhere close over here. So it's not going to be to sketch, but let's say it will be 1, 2, 3. Let's say I make it going this way, so this way, where V3 is the value we just calculated. And now the last one looks like it's easy. It's a compression again, and at constant pressure. So basically it means we just go through this line of constant pressure back to the initial state. Alright, so I think we have all the information we need to solve the problem. If not, we can always add some calculations. So now step 2 basically will be to see what is the value of the work. So every time we need to calculate the work, we need to decide about the convention we're going to be using. So we're going to be using the one which is Q minus work equal change in energy, in which case the work done by the pressure is positive PdV. Alright, so using that relation over here, so step 2, the main equation we are using is what? Work equal to PdV. Okay? And we need to do that for each one of the processes. So let's see, let's say process 1, 2. So process 1, 2. What do we know? We know this one is PV equal to a constant, so that P will be equal to C over V. So that means that we have here C over V dV. So that gives C dV over V, which will be work 1, 2 equal to C log, and now we'll put the values. We should have here V1, V2, V1, V2. So this is going to give us log V2 over V1. And C can either be P1, V1. So C can either be equal to P1, V1 or P2, V2. So in this case, let's say that work 1, 2 will be equal to P1, V1 log V2 over V1. Okay, and if you do the numerical calculation for this one, you are going to get that is equal to 37.18 kilojoules. Okay, so now we follow the same procedure for process 2, 3. So again, we use the equation work equal to P dV, and in this case between process 2 and 3, so I need to go back to my first page. 2 and 3 we know is a polytropic process equal to a constant. Alright, so that will mean here that P equal to C over V 1.2. Okay, so again I'm going to do a derivation because I think it's important to understand how to do the derivations, but again, if you know the expression right away for the polytropic process for the work, you can do it. Okay, so what do we have over here? This would be equal to integral of C dV over V 1.2. You can write this as C V minus 1.2 dV, which will be equal to what? C, and once I integrate this, what do you have? You have V of minus 1.2 plus 1 divided of minus 1.2 plus 1, and the limits of integrations in this case will be V2 and V3. So this gives 1 of 1 minus 1.2 C V3 to the minus 1.2 plus 1 minus C V2 to the minus 1.2 plus 1. Okay, whereas before, in this case, we know that PV to the 1.2 equals C. So that means that C could also be equal to what? P1 V1 to the 1.2 or P2 V2 to the 1.2. So if in this case here about 2, 2, 3, 3. So we can take here P3 V3 to the 1.2 and this one to be equal to P2 V2 to the 1.2. So you do this, you can see that this term here will cancel with this term here will cancel with this term. So basically at the end you have that the work 2, 3 is equal to 1 minus 1.2 P3 V3 minus P2 V2. Okay, so we do the numerical application. One, two. So let's see. P3 is equal to P1, so it will be 2000 times V3 we found to be equal to 0.0169 minus P2, which is 500, times V2 that we found to be equal to 0.0536. So if you carry out the numerical integration, you find out this should be equal to minus 34.86 kilojoules. Okay. And finally, we do the same thing for process 3.1. This one should be a lot faster, it's constant pressure. So use the same expression, PdV. In this case, P P3 equal P1. So actually here you see on this figure P4 really is P1. Okay. So we get that work 3.1 would be equal to, let's say, P1 dV. So it would be equal to P1. And what are the limits of integration? We need to be careful here because you go from V3 to V1. So this will be V1 minus V3. Okay? So we do the numerical application. Work 3.1 will be equal to P1, which was equal to the 2000 megapascals, so that would be 2000 kilopascals, times V1 0.0134 minus V3 0.0169. So that gives us a work for work 3.1 to be equal to minus 6.97 kilojoules. Okay, so basically we have all the information we need. So step 3, not needed. And we can go to step 4. That is what? So the total work during the 3 processes will be equal to work 1,2 plus work 2,3 plus work 3,1, which we had what? 37.18 on the first one, then minus 34.86 minus 6.97, which gives a total work of minus 4.65 kilojoules. All right, so what does that mean with our sign convention? So remember, this is our system. Okay, so when you use this sign convention over here, use this equation, the sign convention is heat going in positive, heat going out negative, but work going in will be negative and work coming out will be positive. So what does that mean? Which makes sense. If you have air and you want to compress it, what do you need to do? You need to go and push, no? So basically you need to put work into this closed system over here. All right, thank you.